We are in a very interesting juncture of discussing Hartree-Fock equations and how they are solved using self consistent fields. We have learned what Hartree-Fock equations are. We have written the Hartree-Fock equation for helium atom, right, and while doing that we have invoked this effective potential energy of electron 1 at its position R1 due to the presence of electron 2, and we have written it as integral phi R2 phi of R2 star multiplied by phi of R2 divided by R1 to d tau. Okay. Well, I should say dr2 not d tau. Okay. What does this mean? It means that phi star phi, that is essentially charge density. What is the charge density? That is given by phi star phi, and the distance is r12. So, that is the interaction between a charge cloud and a point charge, right. That is the electron repulsion. Okay. Electron number 1 is taken as a point at r1, electron number 2 is taken as a cloud. Okay. You get similar expressions if you think of say ionic atmosphere in solutions of electrolytes, okay. Very similar kind of thing. Okay. And then using it we wrote this effective 1 electron Hamiltonian for electron number 1. The change that we see in this 1 electron Hamiltonian is the incorporation of this effective potential energy due to electron repulsion that we have discussed just now. And with that we wrote down Schrodinger equation as usual. We said this Schrodinger equation is called Hartree-Fock equation. We also said that Hartree-Fock equation is obtained from variation principle by defining energy like this. Take the wave function as a product of two orbitals, work out the expectation value of energy using the Hamiltonian for helium atom. So, we have not explicitly used that effective potential here, okay. Eventually we will reach the same place, okay. But this is just what we know for a long time, okay. Then we expand it and some of the double integrals become a single integral. One remains a double integral, that is called J12 the Coulomb integral. The other ones which essentially give your 1 electron energies for electron number 1 and electron number 2, they are called I1 and I2. So, what does I stand for? If I write a general index I for 1 or 2, that would give me a energy of a 1 electron system, and J12 is the electron repulsion term, okay. That is what we have, that is how far we got in the last class. Now we learn how to invoke what is called self consistent fields and try to solve these equations, okay. This is the beginning of a very what should I say, ubiquitous technique that keeps on coming back in the field of computational chemistry, okay. But we will talk about that in a more appropriate time. For now what we have is we have this orbital, well, product of orbitals, that is a wave function that we have said. So, we are working under orbital approximation, and so if I may remember you, the way Atkins puts it is very nice. Atkins says that the meaning of this is that each electron is in its own orbital, right. So, electron number 1, its coordinates are defined by its coordinates only. Electron number 2, well sorry, what am I saying, its wave function is defined by its own coordinates only. Phi is only a function of R1, nothing to do with R2. Phi of R2 is only a function of R2, nothing to do with R1, right. So, we are pretending as if the electrons move around in whatever way they move around, that we cannot really talk about trajectories, but their movement, of course there is a repulsion and the wave function gets corrected and all that, but then they move around as if the other one is not even there. When they come close together they repel each other, when they go far away they repel each other to a lesser extent, alright. But there is no correlation in the movements of the two electrons. That is what orbital approximation essentially suggests. Whether that model holds or not, let us hope we will get there by the end of this class, alright. And we have talked about the Hamiltonian already. We make this Hamiltonian operate on this wave function and we get this equation, and the first question that we will answer actually is what is epsilon 1, alright, and this is the effective potential that we talked about earlier. Great. Now let us think a little bit about what the functional form of this R dependent wave function should be. Well, not R dependent, capital R, remember, is combination of r theta and phi. So remembering what we had done for hydrogen atom wave functions, we can write it as a product of an R dependent part and a theta phi dependent part, capital R multiplied by y. So capital R would lead to a quantum number n. The only thing is that eventually n becomes a variational parameter, and the theta phi dependent part is associated with the quantum numbers L and m. So the moment I write it like this, I have to do something to the Hamiltonian, right. I should actually write the Hamiltonian in terms of spherical polar coordinates also, and if you remember what we did in case of hydrogen atom, we had showed you 13, well we rushed through 13 slides which we did not discuss, and that tells us how to generate the Hamiltonian in terms of r theta and phi, and then we did separation of variables. So when you do all that, I am not going through the steps again, they are quite mundane and you do not have to remember the steps, you do not even have to remember the final answer, but I hope you will not have problems in believing me if I write that the equation that we end up with for the r dependent part, and we do not bother about the theta phi dependent part because we are discussing helium. In case of helium ground state, only 1s orbitals are involved, they are theta phi independent. So who cares about theta phi right now? So we get this equation in r dependent part, the first term and the second term. In the second term, remember what this L into L plus 1 is, that is beta. If you remember the separation of variables in case of hydrogen atom that we had performed, this beta turned out to be that L into L plus 1. Okay. So exactly similar treatment, but for helium, not for hydrogen. Okay. This is what we have got. Okay. Then what have we got here? This r of r1 is a wave function in terms of one coordinate, that is r1. Then we have something like energy epsilon or epsilon 1 that we have written here. I have forgotten write that subscript 1. And we have an operator. That operator essentially, what is the operator? Some differential DDR kind of thing is there. So it is a differential equation. So this is a time when we should be really happy and say, hey, we got a differential equation, we have solved so many, or well, at least we know the solutions of so many. This can be solved as well, look up a book, it can be solved. There is a problem. The problem is that in this differential equation, in the operator part itself, you have a contribution from the wave function, and that sort of lands us in a little bit of a fix, because how are we supposed to get the wave function? By solving the equation. But then how do you solve the equation if the wave function is sitting in the form of the operator itself? So this is sort of a egg and chicken problem. Which came first, egg or chicken, or is the egg inside the chicken, or what? So we got a problem. We cannot really solve it as easily as we solved the differential equation for the hydrogen atom problem, but we have come a long way from hydrogen atom problem already, and we know many ways in which we can at least have an intelligent guess of wave functions. So since we do not know what the wave function would be, and that knowledge is required in order to write the Hamiltonian itself, we can make an intelligent guess, and we have already discussed at length how many different kinds of trial functions are used, and these what we discussed are actually very classical kind of trial functions. There are many more that came later. So we make an intelligent guess of an appropriate wave function, and then we evaluate this U effective with it, okay. That now becomes a number. Now you can solve this this particular differential equation for the trial wave function. What do you get? Now you get a new set of wave functions. Will they be exactly the same as the trial wave function? Not necessarily. This is the beauty of this technique. So you guess some function. So what you are doing essentially is that you kind of come up with a rough model of the potential energy. With that, solve this Schrodinger equation kind of thing and get what the wave function is. That wave function will be for the system that you have modeled using that rough potential energy, and mostly that wave function that you generate is going to be slightly different, usually not very different, but slightly different from the trial wave function. Okay. So, solve the equation and to get what I call improved values of wave functions that are closer to reality. Okay. What do you do then? Well, do it again, right. Now, using those wave functions, newly generated wave functions, plug them into the expression for the effective potential, write the equation once again, the Hamiltonian will change, solve it, the solution will also change a little bit most likely, and you are going to go towards better and better and better match to the reality of wave function. Remember building that elephant? Perhaps you start with a mouse, the wave function that you choose, and slowly as you add terms and all, that mouse becomes fatter and fatter and fatter, starts looking like a pig, and then like a tapir or an anteater which has a small snout, and finally it looks something that is close to the elephant, maybe a little thin elephant since you started from a mouse. So, that is the idea. Okay. So, when there is not much of change in successive iteration, then you have what is called self consistent field, right. The field that you have generated is now self consistent, and that is as good as you can get using the wave functions that you have chosen to work with, right. So, the orbitals that you thus generate are called Hartree-Fock orbitals, right, and usually the guess function that you use are linear combinations of Slater orbitals, right. Remember construction drawing of elephant problem, there is no restriction on how many functions we want to use, how many coefficients we want to use, we just play around with them until we get a suitable match. So, you see you may not end up getting a proper basis set to start with. Suppose you start with one Slater orbital, I mean you might get what looks like convergence, but that may be far away from reality. So, you want to increase the number of terms. Okay. So, it is not just iteration with one trial function, you want to play around with trial functions as well. That is what makes it a numerical computational problem. Okay. Analytically, if you want to do it by hand, it will take ages and you will get frustrated and not do it, right. That is why you want computers to do it for you, and that is what leads to this very sophisticated software that is written and is now available, some for a charge, some in free domain, in which with which you can do this computational chemistry calculations, and their choice of basis is of utmost importance. Not all bases work equally well for all problems. So, here at our level for now we talk about linear combinations of Slater orbitals as the initial guess, and then we keep on using this self consistent field method until we get convergence. Okay. This is called the Hartree-Fock-Ruthan method, which we might mention in the next class. I am actually in two minds because we are running out of time. We want to talk about molecules, not much time is left, but we have to finish what we started. So, let us see. Okay. That being established, we want to now focus on this chap epsilon 1. Epsilon 1 looks like energy, right, and we get it by as an eigenfunction of an equation that looks like Schrodinger equation, one electron Schrodinger equation. Is it energy? Is it energy of the atom? Is it energy of the orbital, or is it something else? What is it? To know that, it is called orbital energy, right. Its expectation value is called the orbital energy, and this is how you define it, of course. Now, how do you evaluate this? Again you can expand it. So, this will be integral phi of r1 star multiplying minus half del 1 square operating on phi of r1 plus integral phi of r1 multiplying this u1 effective r1 and so on and so forth. So, what you get is, sorry, I forgot to say that in the first integral you will include this minus z by r1 as well. Since I forgot, I will write. So, this becomes integral phi of r1 star. Please do not forget that when you write a wave function in the bra vector, you are writing its complex conjugate. That is minus half del 1 square minus z by r1. So, this is a Hamiltonian that you would get for a one electron system, pretending as if there is no other electron that operates on phi of r1. That is my first integral. The second integral is integral phi of r1 u1 effective of r1. There is no need to write that bracket, phi of r1, something like that. So, essentially you get J1 I1 plus J1 2. Okay. I hope it is not very difficult for you to see that this U1 effective actually contains this phi r2 star 1 by r12. You might be wondering the way I have written it here in my bad handwriting, how am I equating this to J12? That is because you have to plug this in there as well, right, U1 effective of r1. So, all this will go in there, that is how you will get it. Great. Now, is this the energy of the helium atom? Actually it is not, because if you remember what we discussed earlier, energy of helium atom turned out to be I1 plus I2 plus J12, right. Remember that variational treatment that we did before this, that is what we get. So, it is not the same as epsilon 1. So, epsilon 1 is not really the energy of helium atom. So, what is it? Subtract one from the other, epsilon 1 turns out to be E minus I2, or I can write E equal to epsilon 1 plus I2, something like that, whatever way you want to write. What is I2? Remember what I2 is? I2 is the expectation value of energy for helium, right. Helium? No. Expectation value of a one electron system with the same atomic number as helium. What would that be? Helium has 2 electrons. So, if I remove one of those electrons, I get a one electron system with the same atomic number as helium. What is that? It is helium plus ion. So, this I2 essentially is the energy of helium plus. Okay. Same way you can define I1 also. So, but there is a catch here, it is energy of helium plus, but using a Hartree-Fock orbital, not using your hydrogen atom orbital, okay, using a Hartree-Fock orbital that we have discussed. So, if we just plug that value, what does it turn out to be? So, ionization energy, right, this minus epsilon 1 turns out to be the ionization energy of helium. What is ionization energy? Energy of He plus minus energy of your helium atom. So, essentially it is going to be minus of right hand side. So, minus epsilon 1. So, we see that this epsilon 1 that we got, well, the negative of that gives us a good measure of the ionization energy of helium, and that is the celebrated Koopman's theorem. Okay. Do not forget that the approximation that we use here is that the same set of orbitals can be used for neutral atom and the ion, which may or may not be correct or necessary. But then when you do a calculation, this is from Clementi's work of 1965, the value of ionization energy that we get is 0.919796 atomic unit, and from experiment it is 0.904 atomic unit. So, not very bad actually. Okay. So, Koopman's theorem is something that forms a cornerstone in discussion of quantum mechanics of many electron systems. We end the discussion today with another very interesting, perhaps intriguing concept, and that is of correlation energy. Remember, we had touched upon this a little while ago. We said that the moment we use orbital approximation, we essentially are saying that the electrons are uncorrelated, the motion is uncorrelated. their expressions might get modified a little bit, of course they repel each other, but they move in the same way as they were moving when the other one was not present. Okay. So, all this Hartree-Fock calculation that we do is for uncorrelated electrons. Okay. So, the energy that we get doing the calculation is minus 2.8617 atomic unit. When we do a more exact calculation, when I say exact calculation, of course you cannot solve it like that, but when you go back to what we had discussed a couple of classes ago, that perturbation theory using 13th order perturbation, or that variation method using a large number of terms like 1000 something terms, remember. Then the value that we had reported, or not reported, the value that we had seen at that time was minus 2.9037 atomic units. So, this is as good as it gets. So, using Hartree-Fock method, the energy that we get is more than that, minus 2.8617 atomic unit. Okay. But then see, it is more not because we have not tried to account for these repulsions and all. We have actually worked very hard, right. We have tried to modify the wave function, we have tried to play around with the field, right. We have done SCF calculation. So, the only thing that we have not done is that we have not considered the correlation between electrons. We have not considered that motion of one electron can affect the motion of the other. What does it mean? You know, sometimes celebrities do not like each other, right. So, in a party, if the moment one celebrity enters, another celebrity leaves by the other door, that is correlation. Two electrons behave like that in an atom. So, otherwise they would move in whatever way, but now if they happen to come close together, if they see that they are going to come close together, maybe they avoid each other, that would be correlation. And what we are saying is that this difference in energy, what is the difference in energy? Correlation energy turns out to be minus 0.0420 atomic unit. You think that is a small number? It is not. It is like 1.14, well minus 1.14 electron volt, significant for the systems that we are talking about. So, what we learned from here is very interesting. Electrons are the celebrities of atomic world. They find a way of avoiding each other when they are in the same atom, and the energy that they save by avoiding each other is about 1.14 electron volt. You get what I am saying? If we do not account for correlation, then the value that I get is minus 2.8617. When we account for correlation unknowingly, when we do those exact calculations, we are not really explicitly saying that okay, electrons are correlated. All we are doing is that we are trying to minimize the energy, and your upper limit theorem tells us that you can get as close to the actual energy as possible, and actual energy would involve correlation even though we cannot calculate it, right. So, the difference gives us the correlation energy. So, electrons, these 2 electrons of helium end up saving 1.14 electron volt energy for the atom by moving in an intelligent manner and avoiding each other. I strongly suggest that you also read this. We have followed Macquarie's approach, but please also read this from Pillar's book. Their notation is a little different. So, you will have to go back and read a little more, and in fact they have used something that we thought we will discuss, but then for the want of time we are not getting into. They have used something called virial theorem. Okay. And using virial theorem they have reached the same conclusion, and they have used some very nice language which I have now forgotten, but it essentially says electrons in that atom find a way of avoiding each other, smart particles, right. That is the, in my opinion, most interesting thing that we have learned in our discussion today.